So let's talk about enzymes. First of all, what's an enzyme? It is a catalyst, but are all catalysts enzyme and are all enzymes catalysts? Be more specific then. What's an enzyme? It's a protein that acts as a catalyst. So it's a catalytic protein. Notice you guys learned in the last set of material that proteins can serve a whole lot of functions. We're going to look at just one of those functions, and that is catalysis. And so your enzyme are proteins that act as catalysts. So in this case, if we look at a typical reaction, we're going to plot Gibbs free energy versus the reaction coordinate. If you look at the one on your handout here, this just allows us to follow the energy profile as we proceed from reactant to product. So as we proceed from reactant to product. If you look here, then the difference in energy between reactant and product, what do we call that in this kind of a graph? Ooh, don't go there. We haven't got there yet on the activation energy, but just from reactant to product is the change in G. That's just delta G. Cool. So for the reaction I've got listed here, is delta G positive or negative? Positive. So we can deal with three situations when delta G is negative, when delta G is positive, and when delta G equals 0. So what does it mean when delta G is negative? So what we use is exergonic. What does that mean? Yeah, it's spontaneous. It will release energy as it happens. Those are the kind of reactions that are spontaneous. So exergonic is going to be synonymous for a reaction that is spontaneous. What about when delta G is positive? So it requires the input of energy, and what's the name we give for that? Endergonic. And in your Gen Chem class, you learned that these are the reactions that are not spontaneous on their own. They need help. They need some outside source to make them happen. So we'll see some different ways to get around this in a little bit. And what is true when delta G equals 0? Yeah, you're at equilibrium. That reaction's not proceeding in either direction overall. It's actually still going in both directions in many cases, but at equal rates. So, but no net conversion of reactants to products or products to reactants at that point. Cool, so for this reaction, delta G is positive, and so we see that would be an endergonic reaction. It is not spontaneous. So we'll see later that I can couple this maybe to some other process that is spontaneous, that is more spontaneous than this guy is non-spontaneous, if you will, to get this thing to happen. So but in and of itself, this is non-spontaneous. So, but there's another part of this profile we got to look at that's important. So what do we call the top of the hill here? So transition state, often symbolized with a double dagger. So we'll call it transition state. In Gen Chem, you might have also heard it called an activated complex. We're going to go with transition state, usually again symbolized by that double dagger. So the important quantity really relevant for this chapter is from where you start to the top of that hill. And what do we call that? That's your activation energy. And in the past, you might have seen that as E sub A. You might also now see it also called delta G double dagger. That delta G double dagger means the same thing as activation energy. It's just the Gibbs free energy from your reactant up to the transition state. So delta G transition state, same thing as activation energy. Cool, higher the activation energy, slower the reaction, lower the activation energy, faster the reaction. What does an enzyme ultimately accomplish here? Yeah, we get an alternate mechanism for that reaction to occur, and we get a lowering of the activation energy. So in green here, this might be the catalyzed enzymatic process, whereas in black here, the uncatalyzed process. Notice a couple things to note about your enzyme. Does it change delta G for that reaction? No, it doesn't. We'll see in a little bit. We'll pull this up now. We'll come back to it. But delta G standard is related to your equilibrium constant. So, and if your delta G doesn't change when you add a catalyst, what this ultimately is going to come down to is that your equilibrium constant doesn't change either. So we're not shifting the equilibrium either way by having an enzyme present, by having a catalyst present. We're just getting it to equilibrium, say, faster. So notice the cell is manipulated to keep most of the conditions not at equilibrium all the time. Notice if I had a situation where reaction reached equilibrium, and then I threw an enzyme in there, what would the enzyme accomplish? So if the system already reached equilibrium, what does an enzyme accomplish at that point? Absolutely nothing. So again, an enzyme doesn't shift the equilibrium either way. It just gets you to equilibrium faster. So if a reaction has already reached equilibrium, an enzyme is worthless. Are enzymes worthless in the cell? No. Then are the conditions usually at equilibrium in the cell? No, not usually. And so usually the cell manipulates conditions to keep them out of equilibrium so that we can have reactions that are spontaneous. We'll talk more on that in a little bit. Cool. Let's talk a little more about enzyme kinetics. So typical reaction has a very simple kind of looking what we call rate law. And typically it's the reactants that show up in that rate law. In a little bit, we're going to talk about and just isolate ourselves to talking about a reaction that has a single reactant. But for now, we might have a reaction that maybe has two reactants, two substrates, if you will. And so in this case, this is what a typical rate law would look like. So what's this little lowercase k called? Rate constant. And what are these exponents here? Orders. X is called the order with respect to A. Y is called the order with respect to B. So, and if you add them together, you get the overall reaction order. So X plus Y in this case would be the overall reaction order. It's just some things from Gen Chem that you got to remember a little bit. Cool, so rate laws. These orders are typically integers in most of the stuff you'll ever see. 1 and 2 are the most common. But 0 happens every once in a blue moon. And we refer to that as 0 order, first order, second order, so on and so forth. Now, do these have to actually be integers? Turns out they don't. So sometimes when you go to study the kinetics of a reaction, you'll get something like 1.5 or even like 1.376. It's really random. You guys will probably never see that. I just want you to be aware of the fact that they don't have to be integers. But everything you're likely to ever see will be integers. So, and it deals with the fact that these are often related to how many molecules are involved. So in the reaction, and usually often not just in the whole reaction necessarily, but maybe in the rate determining step. So if I was to ask you guys a question, how long would it take for me to get to the restroom from here? It's just right across the hall. How long do you think it would take me to get there? I ran. 3 seconds? Sweet. Actually, you really can't give me a definite answer. I told you I was going to run, but I never told you how I was going to get there. So what I didn't tell you is I'm stopping by Zimbabwe on the way there. Catching a plane, chilling in Zimbabwe, coming back, and then going. So it might take me a few days. So here's the deal. Unless you know the pathway, which we call the mechanism for reaction, it's really hard to make any concrete determinations of these orders. So we usually study some kinetic experiments to come up with these. So, or if somebody's already done the experiments and come up with a mechanism, we could use that mechanism to figure it out as well. And we'd look at the slowest step in that mechanism and then go from there to figure out what these are actually going to be. You know, if it turns out A wasn't involved in the slow step, it may not even show up here. That could be a 0. And what's anything to the 0 power? 1. And anything times 1 is itself, so it just kind of goes away. Or maybe, you know, there one molecule of B showed up in that slowest step, and so maybe this would be first order. And that's kind of generally how it, you know, there's a correlation there. But unless you know the overall mechanism, the pathway the reaction's taken, you may not be able to do this. So, and we get kinetic data to figure that out. So notice these do not have to be the coefficients in a balanced reaction. They sometimes are, in fact, a lot of times they are, but they don't have to be. Cool? So where do we get these orders from again? Experimental data or a mechanism. And where would somebody get a mechanism from, though? From experimental data. So ultimately, it all comes from experimental data. Sweet. Let's talk about enzyme kinetics now a little more specifically. So enzyme kinetics. So if we look, there are two kind of common models that are used, and one's a little older than the other, and that's this guy. That's the lock and key model, the lock and key model. So before we look at this, though, we need to look at an overall principle of the universe. If I let this marker go, where's it going? To the ground. Why is it going to the ground? Gravity. Notice, what is gravity? What is it? It's a force, but it's a force of attraction between objects that have what? Mass. Sweet. The marker has mass, the Earth has mass, great, they love each other. So, and notice, as you let something go where it's attracted to going, what happens to its potential energy? It decreases. So when things form attractive interactions, it lowers their potential energy. This is super, super, super important. So things form attractive interactions, it lowers their potential energy. So with this lock and key model, so the idea is that your enzyme, so it might have a certain shape. So based on, the amino acid sequence and the tertiary structure, and maybe even quaternary structure, depending on the enzyme, and that out there is some substrate that perfectly fits right into that, like a lock and a key. And apparently my drawing is terrible, but that's supposed to represent fitting in there perfectly. So here's the problem, is that we look at this idea of enzyme catalysis, and what we realize is that binding happens first. You've got to bind the substrate first. And once you bound the substrate, then you can catalyze the chemical reaction. And so this lock and key method, the lock and key would describe the binding. And if this is an awesome fit, why would there be an awesome fit, by the way? Because they're attracted to each other. Why would they be attracted to each other? Electrostatics, all sorts of reasons, hydrogen bonding, dipole-dipole, all those lovely reasons we already studied with protein structure, they can be involved right here as well. So at what we call the active site. But if things go where they're attracted, what does that do to their potential energy? It lowers it. And that's a big problem with this model, because if you look at binding, what you find if you kind of plot the energy going on here is that this might actually lower the energy before it goes back up to complete the reaction. And so in this case, because I had a nice, really good fitting lock and key, it lowered the energy of the enzyme substrate complex when they're bound together. What does that do to the activation energy of the next step, the catalytic step? Makes it higher. All of a sudden now I've got a much higher activation energy as a result. Is that what enzymes do? No. And so the lock and key method, it's historical. We keep it around because it's interesting. But it's kind of an outdated, antiquated model now. We don't use it too much. What's the much better model that we commonly deal with now? Yeah. You might see it in a couple of different, if I can spell it. And I should look on the correct paper, see what I called it there. So, here. We'll go back and call it what it's called on your paper. Instead of transition state there, I'm going to call it induced fit. What is the basis of this induced fit? It's not that they form a perfect fit right away. They kind of fit, kind of don't. What is the basis, though, of induced fit?
Proteins can fold in 3D space.
Good. Proteins can fold in 3D space, and they're flexible. Protein structure is flexible, and that is the key to induced fit. They're flexible. And so when the enzyme and substrate bind together, it's not a perfect fit right away, but maybe that causes the enzyme to change its shape a little bit so that you end up with a better fit later on. So, and the idea is that rather than lowering the enzyme substrate complex in such fashion so far, it's not such a good fit anymore, but what it does is it lowers the transition state's energy instead. So that's the induced fit model. And again, what's the basis of this? Flexibility in the protein structure. Flexibility in the protein structure. Cool. I didn't mention this before, and it just dawns on me that maybe we want to talk about this for just a second. We talked about enzymes earlier, and we kind of plotted Gibbs free energy versus what's called the reaction coordinate. Cool. Whenever I let something in the universe go where it spontaneously wants to go, what happens to its potential energy? Goes down. And so if two things are attracted to each other, if I let them come together, that lowers their potential energy. Keep that in mind. So binding, because it's attraction, lowers potential energy. So in this case, if I want to catalyze this reaction, what energy do I actually want to lower? Do I want to lower the reactant's energy? No. Do I want to lower the product's energy? No. What do I want to lower? Transition state's energy. And so in the induced fit model, it's convenient if the enzyme is designed to actually bind the transition state. It's an induced fit. The enzyme kind of binds substrate, but it really binds the transition state. That's what it really, so it changes the, kind of binds substrate, then changes shape to really be in a place to bind the transition state. And by binding that transition state that's forming, it's helping it to form, because by binding it, that's attraction, what's happening to its energy? It's lowering it. Do you guys remember drawing out transition states in organic chemistry? And you can kind of, here's the reactant, here's the product, and somewhere in between, that's what a transition state might look like with little dashed lines and stuff like that. You guys did that. It was a great exercise, and you're like, why did we do that? Well, you kind of look at, the stability of that enzyme and stuff like that. Now, a couple things. If your transition state is charged, let's say your transition state's negatively charged. Well, great. I'd love to have a positive amino acid in that active site there as well, because the interaction could lower the transition state's energy. So that's another way the electrostatics can play a role as well. But also, this is a great way to make inhibitors. If I kind of have an idea with dashed lines and that whole exercise you guys did in organic chemistry of what the transition state looks like, then I'm like, I'm going to try and make a brand new molecule that looks just like that. What would I call that, brand new molecule I make in the lab that looks just like a transition state for a certain reaction? Transition state analog. Transition state analog. So in this case, let's say I made a transition state analog to lollipops. So lollipops bind to my lips, and then there's this new molecule somebody synthesized, and it looks a lot like a lollipop. Has the same, polar groups in the same places in similar ways as a lollipop. And when I see that thing, what's going to happen? I see lollipop, I'm like, sweet lollipop. I'm like, oh, kind of looks like a lollipop. And what kind of inhibitor might that transition state analog act as? Competitive. So I just wanted to bring that up way back at the beginning. I meant to mention that earlier, but we can make these transition state analogs. We kind of have an idea of what those transition states look like. Sweet. I can make an inhibitor for that enzyme. I'll make a molecule that looks like what I think the transition state looks like, a transition state analog, and they act as competitive inhibitors.